All right, welcome back to Godot coding challenge number 2, the Menger Sponge Fractal. Menger Sponge Fractal is a relatively straightforward fractal. You kind of just take a cube and you split it into segments, or a square in 2 dimensions. Split it into segments so it's 3 in each dimension. So for example, here in this 3-dimensional cube, we said that there is a split along this axis, and as well depth-wise along this axis. And that gives us, well, 9 in the case of 2 dimensions, or 9, 18, 27 cubes per split in 3 dimensions. But what makes this fractal interesting, or at least more exciting than just a cube that gets chopped into smaller bits, is every centerpiece within those splits here gets removed. So that gives it kind of a sponge look. So if you were able to take a camera and fly it around, you could fly around the sponge and kind of explore the inside of this cube based on the fact that, yes, we split it into smaller chunks and we remove pieces from it. So once again, this is based on the coding challenge number 2 from the coding train. Go check it out. They go through how to create this in processing in JavaScript or whatever. And it's a really great video. I recommend you check that out first, and then you come back and look at this one, just because you'll see how to do it in a more lightweight framework versus doing it in the Godot game engine. So to get started, we're going to, hold on one second. We're going to create our new Godot project. So I have Godot up and ready to go. Make a new project. I'm just storing this in a temporary folder. We'll call it Menger. Create the folder and edit it. So because we're going to do this in 3 dimensions, we're first going to create our 3-dimensional scene that is just the cube itself. Now the cube is going to know how to render itself in 3 dimensions. It's also going to know how to split itself into even smaller segments. So to do that, we're going to need to create a spatial, and we'll just call it sponge. All right, we'll give this sponge a script. All right, let's save it first. Give it a script, same thing, create, and we've got our spatial here. Now, just before we get started, we also want to make sure we set up our debug environment so that we can, at the very least, take a look at this sponge. So even though it's invisible now, let's just start by giving it a little dummy mesh instance. And this mesh instance is going to be a basic cube. So new cube mesh, really simple. We'll save it. And just as an example, if I were to play this scene, we would see nothing. And that's because in Godot, we actually have to set up a camera and lighting to be able to even see it. So we're going to create another scene. We'll just call it fractal. Save that as well. And we're going to give it a single child node called this sponge. There it is. And we're also going to give it a camera. And we'll move this camera away and up and rotate it that much. Come down a little bit. And now at the very least we can see it. We'll deal with moving the camera into a better position later. So now, as long as we use this fractal scene, we can see our cube. Nothing exciting, but at the very least we're set up and ready to go for our work here. So, okay, we've got our sponge, and it is currently a boring cube with a single mesh instance into it. It needs to be able to split into smaller pieces. So the first thing we're going to do is go to our script here, and we're going to write a function called subdivide. Now, the subdivide is going to be very simple. We're going to go over each child mesh instance, which is our current large size cube. We're then going to split that cube into 3 segments per dimension, so 3 across X, Y, and Z. And that is going to, fractalize it into smaller but equivalently formed shapes. So to do that, because we're going to use Godot's parent-child relationship to do this, we can simply just say, go over each mesh instance. So for child mesh in let's do get children. That gives us every single child. We're only going to have mesh instances as children. And we're going to say remove this instance, but use its location to create more. So this mesh here, we want to say we have a mesh that occupies its full space. We want to remove that mesh, and in its place create the child meshes underneath of it that are the smaller pieces with the hole missing in the middle. And then we can use those to later create even more in a recursive faction, which will then give us our infinite fractal, assuming we take that many steps. So the first thing we're going to want to do is loop over each of these dimensions. So we're just going to create some simple for loops for x in range -1 to 2, for y in range -1 to 2, same thing, for z in range -1 to 2. So we're going from -1 to say if we're at the center, we take one step back, that's -1, 0 is the center, 1 is the right side, and we go to range 2 because range is non-inclusive. So this is effectively saying from -1, 0 to 1 in every single dimension. We need to create a new mesh and then position the new mesh and prepare to add the new mesh. So what we're going to do is we're going to say we're going to create a list or a collection of all of the instances that we're going to make. So our new meshes equals just some list. So that way we can create them, have them ready to go, and then pop them into place as soon as we're ready. Now, before we go ahead and make the new one, I'm just going to continue here and say after we've created everything, we want to remove this mesh from all of the children. So very simply, we'll just do child mesh.q free. And what that says is next chance you get, just remove this mesh. It'll destroy itself. It'll remove itself from the parent. We'll basically won't have to worry about this mesh anymore. It'll go away. So here is the meat and potatoes as far as the fractal goes in a basic sense. And we'll want to be able to call this function as needed. So we'll take another quick break. We'll go back to the fractal and we'll say, hey, fractal, we want to be able to tell you that you need to subdivide. So we're going to add a button. Very simple. Add a button to it. This is a control, so it lives in the GUI space, so it's not in the 3D world. But we'll just make it called split. And very simply, we'll give it a pressed. We'll go to the fractal. Oh, we need a script here. Sorry. The fractal. And then we'll say when somebody clicks on the button, which is this pressed signal, we'll go to the fractal script, and then fractal is just simply going to say, hey, sponge.subdivide. So that's going to call that subdivide function on the sponge, which is the one that we just began working here. And for the sake of debug, we're just going to print here. This is going to print a whole bunch of times for every single mesh. Luckily, there's only one, and it'll go away. So let's play this. Let's set up our fractal as the main scene, and let's take a look and see what happens. So here's our thing. We hit split. It printed here a whole bunch of times, 3 for each dimension, and it also queue-freed that that cube, so it's gone now. So now we have it set up so when we press the button, it's going to split. The old cube's going to go away, and now we just have to create the new cubes. So the only thing that's really left to do is, remember, we don't want to create every single cube. We only want to create them if they're not the center one. So what's kind of a neat trick that we can do about this, and they go over that in the previous, the original coding challenge video, is if we take the sum of the x and y position. So remember the -1, 0, and the 1. If the sum is greater than 1, then that means that it's in the center. Oh, sorry. It should be in the center. If it's not greater than 1, then that means yeah. So we'll calculate the sum. Var sum. Should we even make 1 equals, and it's just going to be the absolute, or it's the sum of the absolute values. I should have mentioned that. If it's absolute value of x plus absolute value of y plus the absolute value of z, then if the sum is greater than 1, then that means that we can go ahead and create this. Maybe I've got it backwards. We'll figure that out later. So the next thing we need to do is create a new mesh instance. So var new mesh equals mesh instance dot new, and then we need to give that mesh an actual a shape. In this case, it's this very simple cube. What I'm going to do is I'm actually going to save it as a we'll just call it cube as a resource. It's kind of overkill because it is a default pre-built-in one. But if you wanted to, for example, make a different shape, where you could point to it in that way. So what we're going to do instead is we're going to go back to our sponge and we're just going to export var model. And we'll just do a preload of the resource here, the cube, and just say by default it's the cube. We won't worry about it later. But all that we can do now is we can say new mesh dot mesh equals the model. So now we have a new mesh that just uses this cube. We'll worry about that later. The next thing we need to do is position it. So we don't have to worry about rotation. All we have to do is make sure that's in the correct location. So what we can do is we can get the transform of the original cube and then adjust it based on where we are in the model, or in as far as splitting that model into all those separate chunks. 1 second, please. Okay. So what we can get is the original transform, which is this guy. So store, or we don't have to do anything tricky about that. So let's do the mesh instance. So new mesh dot transform, or we can just do dot position. Oh wait, it's not position in 3D space. It is translation. So we'll go back dot translation, and the X translation, the Y translation, the Z translation are all based on this X, Y, and Z. We'll just be lazy for now and say if it's, so we know if it's at 0, we're going to use the same. If it's at -1 or 1, we want to be 1/3 to the left or 1/3 to the right. So new translation equals, I believe, vector 3, and it is going to be x times 1/3, and we'll just do, let's split it up. X position equals the previous one, so child mesh dot translation dot x. So where the previous one used to be, we then want to take a third step either direction. So we'll do this guy plus child mesh dot scale. I believe it's called scale. Dot scale. Now the scale is going to be identical for all three, but we'll just do scale.x just for the sake of consistency. So we're going to take whatever scale it is. By default, it's 1 because it's the same size as 1. And we'll divide it by 3 and multiply that by the x. So in the case that it's 0, we're just going to stay in the middle. In -1, we're going to move -1, -1/3. And in the case of 1, we're going to move +1/3. And then what we can do is just duplicate that several times, do y and z, do y and z, and do y, z, and y and z. So that gives us our positions of where this new cube should live. So x position, y position, z position. Now, one thing we notice is the scale. So when we chop this fractal up, each cube is smaller by the 1/3 size. So here, this center is 1/3 of the x, 1/3 of the y, 1/3 of the z, and that is going to continue every single time. So then this is a third, this is a third, this is a third, so on and so forth. So one thing we forgot to mention here is scale the mesh, and we're just going to do new mesh.scale equals the old mesh. So child mesh.scale divided by 3. And that just shrinks it down a little bit so it doesn't overlap with itself. Mu. Yeah, mu is not what we're looking for. So we've scaled it down. And then last thing we do is we do new meshes.append this new mesh. And we do that because later, after we clear away all of the previous meshes, we want to add all of the newly created meshes. So with that, we can just do add child, for new mesh in new meshes. We'll just add that as a child to our sponge. So let's see what happens now. So let's take a look. We've got our single thing. We split it. It's split into a smaller one. We're seeing we're getting smaller, but things aren't quite lining up the way we want. And unfortunately, I clicked on it a few times, so now we've got quite a few meshes there. So let's set a breakpoint and debug this and see what could possibly be going wrong. Split. Okay, so we're creating a new mesh. We've got the model. We saw that because the cube returned to its, it stayed there even though the old one got removed. But we need to calculate where the x position, the y position, and the z position are going to be. So let's see what we're doing. So currently, we're setting x, y, and z are all -1, so we're at the top left corner, meaning that the x positions should be -1, -1, and -1. So we got -0.3, which is about right. We're at the -3rd level. And we set its translation there, and we append it. All right, so let's just take a look. And in fact, it might be easier to debug this. Nothing interesting is happening there right now. Let's look at our fractal. We've got our sponge, and we see that we've got a whole bunch of new meshes. We can look at their transform, see how they're, if we look at the translation, they go from -3, -1/3, -1/3, and then this z went from 0, 1, or -1, 0, 1, -1, 0, 1, so on and so forth. And we skip the center pieces, which is great. So the real issue is maybe our scale seems okay. I think our translation is not quite what we're hoping for, and that's probably because we're not offsetting it by the previous translation properly. So what we can do now, just to play around, is I can actually shift this around, and we see here, or let's shrink this a bit. If I mess around with the translation, we move this cube around. So see how it seems to be overlapping with those cubes. If instead, oops, let's widen this just a little bit, move this down. Instead, if I did -0.6, would that have fixed it? Did I get my math wrong? So this would move it off to the side a bit more, which should be fairly accurate. So let's take a look at my math here. So if we're taking it, dividing it by 3, the scale should have also gone down by 1/3. Let's be crazy, just scale it way down so I can take a better look. Split. So this looks right. So by scaling it by 1/6, we're kind of getting a closer thing. If I split it again, we're probably going to run into trouble. Yeah, so now it's split, and it's too small because it's shrinking much faster than it should. But we are getting that sponge shape in there, which means that the translation is the problem. Unfortunately, let me check my notes to see if I missed something. Translation that shouldn't be a problem. Sorry. Either way, we're getting the logic there correctly. It's just that our positioning is not quite what we're hoping for. Moving it over by 1/3 and shrinking it to 1/3 should have done the trick. X, Y, Z, X, 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 Y's across the board, Z, Z's across the board. I mean, let's just do something silly. Let's do it by half and see, because that should move it a little bit further. And there we go. So, oh, you know what? It might actually be working fine. Let me do this one more time. This might have been a time waste. So what might be happening is it might actually be accurate, but because of the camera angle and the way we're looking at it, it kind of looks like, the way the lighting's hitting it and everything, it looks like it's a solid piece. But in reality, what might actually be happening is we're looking through it and seeing the back side of it, and it just appears to be identical. Oops, I'm rotating the camera. Let's rotate the fractal, the sponge inside of it. If we rotated it, oh no, maybe I'm wrong. That sure looks like a single thing. Split. And split. Oh, not right. Oh, did I not save it? Is that why? Oh, that's because it's doing this. Split. And let's just go take a look. I'm going to do that off screen for a second. I'll bring it back in. And I want you to rotate. Yeah, so we're still running that problem where even though I've rotated it. So what we're going to do now is table this for a second and kind of go back to this view here. And it is true that the cube being in one place is not very exciting. So what we can do is simply just take every time a frame happens, let's do our rotation speed equals vector 3, and we'll simply just rotate. I have no idea what a good value is, so we'll just do 30, 30, and 10. And we'll simply do our rotation every single frame, rotate equals rotation speed times delta. And then we'll just take the sponge dot rotation plus equals rotate. So that means that every single frame, it kind of rotates a little bit. That should let us get a better view of it so I don't have to sit here and play around in the remote debugger and edit it way too fast. Let's go just, insert. Let's do 3, 3, and 1, because these might be in radians instead of degrees. So even that is still too fast. We'll do 0.25, 0.6, and 0.6, and let's see how that looks. There, it's rotating. That just allows us to get a better look at it. Also, just while we're looking at it, I'm going to tell the camera, hey, let's move it a little bit closer, maybe even closer than that. There we go. So now we should be able to get a much better view once we get it figured out that, hey, here's our cube. We split it. Now we're finally, did it twice. We finally got it. By the way, our translation here is not quite right. So it should be the previous child's x plus, maybe this is wrong, plus its scale times 3. I'm running out of time here, unfortunately. But you can kind of see how we've got this. Now, one thing I wanted to go over, and I don't want to get too much into this current implementation of it, because one thing I wanted to show was if we look at our debugger, and let's take a look at some of the monitors, we can see that if I look at the frames per second, it's looking okay now. But every time I split it, see how much it takes much longer every time I split. We're waiting here for it to calculate just how many things. It's no longer responding. We're getting to a point where we're creating a lot of cubes and then rendering a lot of cubes. Now that is going to tank the FPS. You can kind of see down here that we're already down to 43. Every time I click it, it's going to decrease the frames per second. Eventually we're just gonna not be able to respond anymore, which is kind of the point where we've already hit, which is a bit of a problem. So the reason why that's happening is we're creating a whole bunch of discrete mesh instances. Usually games don't have exponential number of instances being created, rendered, lighted, etc. But every single one of these instances needs to be, pipelined to the graphics card. The graphics engine says, hey, I need to draw these at some rotation according to, reflect light off of it. I don't want to get into detail of that because I'm not really an expert on it. But the point I'm trying to make is we're creating a lot of instances that are all just a single mesh instance node, and that's got a lot of overhead behind it, and that is going to kill your frames per second, your graphics engines, graphics card is going to work overtime, all for some very simple shapes. And one thing to also note is these very simple shapes are all identical to each other. They might be located in a different position. They might even be rotated, in our case, not rotated, but they might have rotation or very simple changes to them, but the actual mesh object itself is identical for every single one of these. And remember, with the fractal, we're going to have a lot of them. So this is something that Godot runs into and has trouble with that isn't quite the same for the JavaScript engine done in the original coding challenge. But one thing Godot does have is a multi-mesh instance. I highly recommend you check out the multi-mesh instance tutorial. I'll have a link in the description for that. There's also the API for it. But the idea of the multi-mesh, oops, this is the wrong multi-mesh instance. The idea of the multi-mesh instance is you can give the multi-mesh instance a multi-mesh, and the multi-mesh is a basic mesh object that you give it. Here, mesh, for example, our cube that we made, our very simple cube. This guy could be the mesh. And we say, hey, we're going to instance a lot of these meshes, but they're all going to be drawn with the exact same logic, just with different rotations, different translations, very, very basic stuff. What that means is the graphics card can then pipeline all of that together and say, I'm going to draw the same shape over and over and over again, just with minor tweaks to each one of them. That's going to speed things up quite a lot. It's going to speed up that we don't have to create things using the CPU. We just say, hey, multi-mesh instance, here's a whole bunch of translations across a whole bunch of identical cubes. And it also speeds up the graphics card because the graphics card is very good at doing the same thing over and over and over and over again. So if we can tell the graphics card, let's do the same thing over and over and over and over again, it makes it happy. We get a much better frame rate. Performance is improved, and your experience is going to be better. So this is something that can be useful for not just a fractal in this case, but you can use it for maybe a particle system. A rocket engine launches off some sort of a smoke mesh. That is going to perform much better in the case of very large numbers of identical meshes versus instancing a ton of them yourself. So to do that, let's go back and take a look at our sponge. So previously we were using this mesh instance. We were saying, hey, this mesh instance, just split yourself smaller and smaller and smaller. and that has performance problems. Instead, what we're going to do is we're just going to get rid of that, and we're going to create a new node called a MultiMesh instance, and we're going to give it a new MultiMesh. Nothing crazy on it, but we will give it the mesh of the cube here. So we're saying we have a MultiMesh. There's nothing shown in it yet, but the way that the MultiMesh works is that you tell it how many instances you want it to have. For example, 1, 2, 3, 4. We're going to start at just 1 for now. There's one mesh in this MultiMesh, and then it also has a collection of all of the where is the documentation? Why did I lose it? We're going back to the documentation. It's also going to have a collection of all of the transforms that the meshes have. So MultiMesh even has things like random rotation and stuff, and random tilt and scale and yada yada, which are useful for like terrain, landscaping, the particle system I mentioned before. We're not going to worry about that because we want to be very explicit about it. But what we want to do is say we have a MultiMesh and we want to give it a whole bunch of transforms for it to use. Let me find that. Or you know, I probably have. Oh yeah, it has something called set instance transform. So this says you give it an instance. So for example, if we only have the one instance, we give it a particular transform, and the transform is going to be rotation, scale, and translation, just like how we've got here. So we're going to give these transform, this transform object to every single instance in the MultiMesh. So not the most in-depth. I recommend you check out the documentation on it, and that little tutorial I showed you. The links will be in the description. But basically, we're going to go back to this and say, okay, when I subdivide, instead of creating a new mesh here, this logic's going to stay the same. We're not going to use child mesh anymore, so we're going to change our iteration a little bit. We don't have to kill the meshes anymore because the MultiMesh is just a single instance that we're going to reference. And likewise, we don't have to add anything. So there's going to be a few changes there. First thing I'm going to do is grab the MultiMesh equals the MultiMesh instance.multimesh, just so that I can reference it a bit more. And also, we're going to have a collection of all the transforms we're going to have. So for each cube, it has a transform. So we can measure the number of cubes by the number of transforms. And likewise, we can use those transforms to split them into more transforms when we do the recursive function to create our fractal. So we'll call something like child transforms, just an empty list. So when we get set up, we're going to create our first transform. So instead of having one by default, let's just get rid of it. And we'll say when we create this object in the ready function, we'll just create a, oops, that's not a word, transforms, dot append, and we'll give it a new transform. Because a transform is by default 0, 0, 0, no scale, no rotation, no translation, we don't have to modify it. It'll just stay in the middle. And then we're going to create a new function called apply instances. And what that's going to do is it's going to take our child transforms that we have defined and apply them to the MultiMesh instance to give it the number of cubes that we want. So it's going to be a relatively straightforward function. We're going to set the MultiMesh dot instance count to 0. We're going to say clear everything that's currently there. Reset. And then we're going to go through and say for every transform, let's create a new instance. So create new instances for each transform. So very simple. We're going to go, in fact, this is redundant. We can just do child transforms dot size. Don't need to clear it, but it'll be the new size. So if there was 1, now there's 27. It's just going to increase the number of cubes, and then we're going to go through and move each of those cubes to their correct position. So for we'll do index for mesh index in child transforms dot size. So for each mesh, we want to grab its transform var mesh transform equals child transforms and we'll get the one at the mesh index, and then we'll simply apply the transform to the instance. And same thing, we'll do multi-mesh, set instance transform. And that is our bread and butter here. We're going to say, oh, for this mesh index, we want you to have mesh transform. So each one of them is going to be set up according to that transform. So we're not creating new meshes ourselves. We're not adding a ton of children. We're not removing a bunch of children. All that's extra overhead we don't need to worry about. We just want one multi-mesh that does all the work for us. So we can apply these instances, and then we also have the ability to subdivide. So because we can't rely necessarily, oh no, maybe we could use the previous transform basis. Let's do this. Let's for every time you click it, everything's going to shrink by 1/3. So we kind of have a current size. So if our current size equals 1, and that current size is going to shrink by 1/3 every single time. So when we hit subdivide, the first thing we're going to do is shrink it. Shrink everything. So current size equals current size just divided by 3. And then now we're going to go through each of the transforms we currently have, which is representing each of the cubes we have, and say we want to get rid of this transform, split it into pieces, and add those new ones. So we're going to create a new list of transforms. So hold on to new transforms. Our new transforms equals just an empty list. And for child transform in the previous one, so child transforms, we're going to subdivide this transform, add it to the collection. So var new child transforms, and add them, because when we subdivide it, we're going to get a whole series of them, equals, and then we'll make a new function. Let's just call it subdivide child transform, and we'll give it the transform. Okay, so we'll have a function that takes a transform, creates 27 minus the holes for the sponge transforms, and returns that back. And then we'll simply just go and add them to the collection. So for new child transform in new child transforms, we'll just add it to our new transforms list. Oh no, we can do that even simpler. We can just do new transforms equals new transforms plus new child transforms. There's no way to actually extend a list with another list. Instead of doing a loop, we can just use this plus operator on the 2. That just doesn't append it as a new item. It extends the list into a longer one with the items of the other list. So we can make this new thing of transforms. Now at this point, we've created a bunch of new transforms. We want to update the collection of child transforms to be the new transforms. That's the new collection, and then we can apply those instances to the multi-mesh, which once again makes the multi-mesh have the correct number of things and gives them each of those transforms. The next thing we can do is, actually no, that's good enough for now. So all of this logic here is going to move into this subdivide child transform. So func, we'll just copy it, give it the child transform. So now we have a transform. We don't have an actual mesh object or a Godot node. We're using an actual transform. So we're not going to create a bunch of new meshes. We're going to create some new transforms based on this child transform. And we don't have to go over any children or anything. We're just going to go across this list here. No adding childs, no killing childs. And we're going to say, okay, for the range -1 to 2, -1 to 2, -1 to 2, we're going to check, oh, is it a centerpiece? If it's not a centerpiece when the sum is greater than 1, because the centerpiece is going to be 0, 0, 0, or 0, -1, 1, or 0, -1, 1. So the sum is always going to be 0 in the case of a centerpiece. We're going to, instead of creating a new mesh instance, blah, 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 we're going to create a new transform. So var new transform equals transform. And we're going to base it off of the child transform. So its position is going to be centered off of the previous one. So that way we're adjusting it left and right instead of having to find the absolute position of that transform, which is a little bit of a pain, but it's basically we're just going to copy it from the previous transform. So child transform. Now, what we're going to do is we're going to change the origin and the basis of this transform. The origin is where it is, basis is scaling of it. We're not going to rotate it at all. This gets into some funny transform logic. Honestly, it kind of kicks my butt every single time I try to do it. So I'm going to use my notes that I've got here. I'm going to try to explain what's going on. It's really straightforward. Every time you do something a little trickier, just be careful. Make sure you pay attention, read the documentation. You'll figure it out. It's not impossible. It's just sometimes things catch you off guard with these transforms, just the way that basis and rotation and stuff is done. But in this case, it's relatively straightforward. So we're going to take this new transform and change its origin. And now remember, it had the child transform. We're going to copy its origin, which really makes this redundant, but forget it. I think this still helps. Don't worry about it. But we're going to take the origin and we're going to say, wherever you are now, we're going to adjust you by a simple vector of the current x, y, and z, so the -1 to 1, and we're going to move it by scale it by the current size. So remember, we split it into 1/3, so we're going to take the current place, adjust it by a unit vector, scale down to the current size. So just a small 1/3 jump, and then a 1/3 on that, 1/3 on that, 1/3 on that, recursively. And likewise, we're going to change its basis to, we're going to make a new basis, and then we're going to scale that basis based on the a simple unit vector, and we're going to adjust that unit vector by the current size. So I believe that is scaled. Sorry, we're going to create a basis. Scaled gives us a new basis that is scaled from the old basis according to some scaling vector, just the unit vector divided by current size. So remember, the default size is a full cube. We want to scale it down over and over and over again based on the size. So it's not simply just taking the old, the current neutral basis and scaling it by 1/3. We actually have to scale down to the current size because it's getting smaller and smaller and smaller. All of this is now pointless, and simply we're just going to create it or tell the new transforms to append the new transform. And then now we've got a bunch of new transforms based on this old transform, and we'll simply return new transforms. So going over what this code is doing now, first thing that happens on ready is we just create a single instance, single transform, apply those instances. Applying the instances is just going to, for each transform, give us a mesh, which is a cube in this case, go over each transform, and apply that mesh to have that transform with the multi-mesh. Multi-mesh is going to take care of instancing all of the meshes, sending it all to the graphics pipeline. That's all done under the hood. We don't have to worry about that anymore, and we're going to have performance benefits because of it. Our new subdivide function is first going to track the current size, which gets smaller and smaller, but also, instead of worrying about meshes, it's going to create new transforms based on the old transforms, subdividing those old transforms into a number of new transforms, holding on to those. And then once it's got all these new transforms, we're going to hold on to those and say those are now our multi-mesh instance transforms, and we're going to apply those to the multi-mesh. So that way we get new cubes. Subdivide is also a little more straightforward. Same thing, we're going to go from -1, 0 to 1, not do any of the ones that are holes, so the center ones. And we're also going to create a new transform based on the old transform, give it an origin and a basis that kind of is shrinking and taking small steps, and adding those and returning those back. So assuming I did everything correctly, we now have our single cube. When I split it, get index origin. Yeah, that's not a word. Split it. And they're gone. So what did we do wrong? So let's take a look here. We have our transform. We give it an origin, which is the child transform's origin. We give it the x, y, and z. 1 second. Don't mind the guard dog. Okay, sorry about that. So, and then we scale it by the current size, which is getting smaller and smaller. Um, Likewise, we've got the basis. We scale it down by the unit vector, multiplied by the current size, and we append that as a new transform. So hopefully that's correct. Let's take a look at some of my other notes here. I think I know what it is. The current size is currently an integer. If I do this division here, an integer divided by 3 is going to round itself to the nearest integer, which is going to be 0. So we're scaling from 1 all the way down to 0, and we're done. Let's just make it a float, and that means that when we scale it, it's going to do floating point scaling on it, or math on it. And we're kind of getting that same case where it was doing extra, but already we're seeing that, yeah, it was because it was doing the wrong math there. We can keep splitting it. So when I hit split, you can see we're getting this Menger Sponge Fractal. It kind of looks, doesn't look as pretty as the example I had. Where did my example go? It doesn't look as pretty because that's to do the lighting and the material and how it's rendered. We'll worry about that later. But every single time I split it, we're getting a pause. That's because it's going through my recursive function and calculating exactly how many cubes need to be made. But when it's actually rendering, rotating, and playing out, it's not actually that slow, which is great because this is being much slower than I'd like. It runs just fine. That's because we're using the MultiMesh instance. So when here it is with a single cube, here it is with a bunch of cubes that are stacked on top of each other. I'm not really sure why that's happening yet. Maybe I can look at my notes and figure that one out. Not that one. And once again, all of these notes are available on GitHub. I'll send the link in the description. It won't be this exact project we've been working on, but it'll be one that I've cleaned up a little bit more, just so that it has a few more features and stuff as well. I won't go into that though, just so that we don't lose a whole bunch of time. So let me check again what is going on here. So when I split it, here we're getting perfect performance. Split it again, slight pause, but perfect performance. And that's just the value of the MultiMesh instance helping us out. So let me see exactly if I can figure out what's going on here. Or maybe let's do this. Hold on one second. I think I, at this point, got something similar to my notes. Segment, let's take a look. Let's see. Either way, the logic's there. It's just that we're getting the position a little bit wrong. I want to fix that for you guys, so that way we can see it in action. Worst case, I'll bring up my previous one. It's doing the exact same thing. As far as I can tell, there's no difference, so I'm not sure why we're running into that problem. Maybe it's the order we're doing something. New transforms for child transform. Subdivide it. Give it the new list. And we apply the instances. When we apply the instances, we're very simply incrementing the count, going over each instance, grabbing its transform, and applying the transform on that index with the transform. And we start with just a dummy transform. Let me take a look at the object itself. Everything looks right there. It should just all be centered in the middle. And this is all centered in the middle. It could also be this guy. Oh, maybe this is why its extents, it was double the size I wanted it to be. So if we look at this cube, it was a 2 by 2 cube by default for some reason, meaning that I wasn't actually giving it enough space. It should have been the double unit vector, not a single unit vector. We split it, we're good. So it was just the cube mesh was messed up. See how when I hit split, it's almost like perfect. Now it's working great. Sorry to lose so much time on that. And that's something you have to worry about is these default meshes. Always take a look at them, look at their sizes, extents for certain shapes, including any of the 2D shapes or areas for your physics engine. Take a look at those. Um, they're always going to be a pain. But here we've got a whole bunch of cubes, and it's running just fine. If I split it one more time, it's going to be really slow. It's turning every single one of these cubes into 24 more cubes or something like that. At this point, I've got so many objects that I'm effectively destroying my machine. Don't recommend doing that unless you really want to wait. Um, you could set an upper limit. There's a whole bunch of things you could do to clean this up. One fun thing to do, as far as exercises you can do after this, is try to do the inverted. In the repo, I've got the example of the inverted, um, but maybe I can look at things here. Or making it so you can better control how it's rotating, or even make it look a little nicer. But either way, we've got our Menger sponge, and it's performing very well. And I think we can count just how many objects we've got. Vertices. Let me do one more. If we go to the debugger profile, vertices. That's for the raster. I mean, we're not incrementing our vertex memory or anything like that. So either way, we're seeing that our performance is doing very well based on this new implementation using the MultiMesh instance. For things where you're using a whole bunch of the exact same model, MultiMesh is the way to go. Do not create a ton of those. Now, granted, if all of these MultiMeshes were a unique object with unique behavior, you might either have to do something tricky to make these meshes still render using the MultiMesh instance, but have logic tied to something else. Or, I mean, typically you don't have that many things with logic unless you're creating some sort of I don't know, a large scale RTS or anything like that. Chain reaction sort of game, that kind of stuff. Um, but you can usually not need multi-mesh instance for your game characters and stuff like that. This is for times where you need a ton of the same thing that are really not doing a whole lot. Here, they're not doing anything. They're just sitting there. They have a scale. They have a translation. They're not even the ones rotating. It's the object as a whole that's rotating, not the individual multi-mesh instances. So don't have to worry about rotation on those. So there you go. There's your Menger sponge. We're kind of covering how to recursively call a function, go through and create instances, how to set up a project in 3D for debug. Remember, you have to have the camera. We didn't have to worry about lighting ourselves because the environment has a default lighting, but you could also set the lighting to be something else. We also go over how to use the multi-mesh instance for cases where you have a lot of the same instance over and over again. I'll include the documentation in the description, but please, if you can, um, excuse me, um, leave me a comment for any cool ideas you have on this. I was kind of over time on this. I apologize for that. But I wanted to go over how to use the multi-mesh to significantly increase performance on this, because otherwise you're going to run into that performance hiccup that we got previously. So multi-mesh is the solution for this, and hopefully this helped you learn how to use multi-mesh if you're looking how to do it yourself. But it's really simple. It's just a mesh, a number of instances of that mesh, and the transforms for those instances as a basic case. If you'd like to see me do another coding challenge or a derivative of this, if you have a new idea, please let me know in the comments below. Godot has a lot of new opportunities. Like I said, this multi-mesh thing has nothing to do with the previous or the original coding challenge that was done by the coding train. Instead, multi-mesh is a solution that's Godot specific, so that's really why I wanted to show this off. Please help others learn. If you know anybody else who's interested in multi-mesh or you think that people could benefit from this, please subscribe. That makes the channel more visible. That helps more people out. And please share these videos, especially this one, if you know somebody's struggling with multi-mesh or performance with too many meshes. Hopefully it helps them out and kind of goes over why we did this, how we implemented it, and shows it's not really that hard. You just got to figure out how the multi-mesh works in the first place, and it's pretty simple from there. So please like, comment, subscribe, whatever. Give it a share. Let people know about this so that way we can grow the channel and help more people learn how to program these cool things in Godot specifically. So, all right, with that, I think I'll see you guys next time. Bye.